Hi everyone, I'm Sam Ginsberg, and I'm going to be talking about how serverless isn't truly serverless. Serverless is a novel cloud computing paradigm that's taken the industry by storm. It has quickly gained a large following due to its simplified programming model that enables easy horizontal scaling, but it's also differentiated itself in another key aspect: pricing. Serverless offers a unique consumption-based pricing model that charges customers for resources consumed instead of resources allocated. This key difference has inspired many new applications that take advantage of this to build systems that are more cost effective. One important question that comes up is, what are the implications of this pricing model? How does the pricing model affect the underlying infrastructure? As it turns out, consumption-based pricing has a huge impact on serverless infrastructure. Since resources can't be pre-allocated and user invocation patterns aren't known in advance, providers must oversubscribe machines in order to maximize resource utilization. This results in higher performance variation in the platform. This also means that time slices in serverless aren't equivalent to one another, so you don't always get what you paid for. Since we know that serverless platforms sell compute time at a fixed price, and we also know that there is significant performance variation, meaning performance per dollar is not constant, this brings up the question, can we perform placement gaming in serverless? Placement gaming is an optimization method by which customers can shift their workloads to machines with better performance characteristics. For example, here on the slides, it makes sense to shift workloads away from the machine on the left towards the machine on the right to reduce costs. So based on this, we seek to answer two questions. First, how much performance variation is there in AWS Lambda? And is there enough to take advantage of it? And if so, is placement gaming on AWS Lambda practical? First, we conducted a measurement study to determine the viability of placement gaming. We examined three possible approaches to performing placement gaming: temporal, spatial, and instantaneous. Temporal placement gaming is about exploiting the day-night or diurnal patterns in user workloads. The strategy works by shifting workloads from periods of peak data center activity to periods of inactivity at nighttime. Spatial placement gaming also exploits diurnal patterns, but instead of shifting workloads across time, we can shift workloads to a geographically distant region with disjoint diurnal patterns. Lastly, we seek to perform instantaneous placement gaming, where we exploit the variation in performance that exists in a data center at any given time. At any given time, there's some distribution of workloads within a data center, and some machines will give us better performance than others. The idea here is to shift our workloads to those machines. In order to do this, we created 4 benchmarks that use resources common in serverless workloads, such as the CPU, CPU cache, disk, and network. We conducted a large week-long longitudinal study on AWS Lambda with the goal of measuring both instantaneous performance variation and observing diurnal patterns in our benchmarks. In addition, we conducted a second smaller study to observe disjoint diurnal patterns. On the y-axis here, we have the performance normalized to the week average per benchmark, and on the x-axis, we have the date. We can see that there's significant performance variation in the cache and video benchmarks here, as well as visible diurnal patterns. We can see that the execution time goes up and down with respect to time cyclically, with spikes in execution time midday. We also examined the performance stability of each of our functions and found that the CPU-heavy functions tended to be stable, while network performance was highly unpredictable. Here we have our second smaller measurement study. On the y-axis, we have end-to-end execution time, and the x-axis is just the date. We can see visible diurnal patterns in the measurements, but we can also observe that US East 1, located in Virginia, always showed degraded performance in comparison to AP Northeast 2, located in South Korea. This is because some data centers are always more congested than others due to a variety of reasons. When performing spatial placement gaming, this is another factor that's important to take into account. So we've established that not only does performance variation exist by showing the presence of both diurnal patterns and variation in performance at any given time, but we have also shown that performance is stable on short timescales for some benchmarks. The next question is, can we build a system to exploit this in production? First, we can rule out a set of possible workloads which won't be amenable to placement gaming. Applications that perform function chaining, or when a serverless function calls another serverless function, are tricky to deal with since they possibly involve multiple function placements, so we avoid those. Second, latency-sensitive applications won't work well due to overheads. And third, we found that network I/O workloads had too little performance stability to be good targets for placement gaming, so those workloads won't work either. Our ideal targets are batch workloads such as image or video processing tasks because they're relatively long-running workloads that are not latency sensitive. Of the three placement gaming strategies, we focus on instantaneous placement gaming. Even though temporal and spatial placement gaming showed the largest amounts of performance variation, they greatly limit possible applications due to restrictions such as data transfer costs and time sensitivity. For our system, we came up with two strategies: an upfront replacement strategy, where we allocate a bunch of functions and then pick the best performing ones and run on those, and a second opportunistic replacement strategy, where instead we allocate a bunch of functions, and then as we continuously execute our workload, we replace any functions whose performance drops below a pre-specified threshold. For each strategy that we developed, we have to evaluate placed functions to determine which are more suitable for our workloads, and we came up with two ways of doing so. First, we implemented a trivial black box approach where we just execute the function and record the end-to-end execution time. While effective, this strategy adds significant overhead to performing a search for ideal function placements. Our second strategy is a gray box strategy, which is a strategy that takes knowledge of the underlying system into account. We utilize CPU steal time, which is a proxy for server load, as a metric for determining ideal function placements. The core advantage of this approach is that we don't have to fully invoke the placed function, which saves us significant startup time. We evaluated our system on three benchmarks, two of which mimic common serverless workloads, and the NQueens benchmark, which represents a lower bound in terms of what results we expect to get from placement gaming. So here we have a box plot of our results. The box represents the 25th, 50th, and 75th percentiles, with the whiskers representing the min and max results. And the y-axis shows the percent reduction in cost. We can see here that upfront replacement is actually ineffective in all but one case for the gray box method. And fast changing server conditions and benchmark duration result in only one benchmark out of the three that we evaluated getting a significant cost reduction. The image benchmark was shorter in its average end-to-end execution time, which means that it was less affected by changes in performance over time, which likely helped increase the reduction in costs. The gray box strategy also reduced the amount of time it took to find optimal placements, further reducing the chances that the performance of function placements could drift further for this benchmark. It shows that this evaluation shows that upfront placement gaming can definitely work for some workloads with shorter end-to-end execution times, but will not work for all workloads due to changes in performance over time. The opportunistic replacement strategy, however, is less sensitive to changing performance conditions since we are continuously replacing the worst performing function placements. So it was able to perform better for the longer running workloads in comparison to the upfront replacement strategy. We can see here that the average reduction in cost for all three workloads was well above 0% and in fact above 2%, showing that this strategy is more effective at reducing costs across a variety of workloads, including the NQueens benchmark, which again was selected as our lower bound. So we've shown that placement gaming is possible, which brings up the next question. What are the implications of this for serverless providers? Well, both strategies we've demonstrated allocate extra function placements that are only ever invoked once, which results in lower resource utilization for the provider, as well as potential increased function startup times for other customers if sufficiently many customers employed these placement gaming strategies. We leave the solution to dealing with this as a problem for future work. Thank you. And if you have any further questions, please feel free to reach out to me after the talk and also check out our paper. Thank you.